So let's start the second part of the second lecture. We continue to talk about the degrees, but in a very wide sense. I will explain three problems, but it's not so simple. Some problems are pretty amazing. You at a first glance, you don't realize it can be solved using graphs. So let me explain to you this problem. It's not very easy to explain. So suppose we have a mountain. So let's say a mountain. It's a bit strange, right? We have a mountain in this sense. So probably we have some ups and some downs, something like this. I don't know, something like this. Okay. So there are two people, person A and the person B. They are at the same level. Okay. So let's say they start from point A and point S. We have a rule. We hope they can change position in the end. But every step they can move, they have to keep with the same altitude. So what I'm saying is that if this guy moves here, and this guy must move here, something like this. Okay, maybe I draw this a little higher, which is easier, maybe easier. Yeah. I don't know, something like this. Why? Okay, maybe like this. Okay, this is S. So somehow when this guy arrive at here, and this guy arrive at here, for example, and this let's call this point B, and when this guy arrive at point C, which we call a peak, this second guy, he he arrives at for example this point. I don't know. I lost. I don't have too many letters for this. I don't know, something cute. Okay, but after that, he must decrease. He has to decrease his altitude. But in this case, to keep with him of the same altitude, this guy has to return. You see, if he keeps going up, they cannot keep with the same altitude. So it has to return until maybe this point. For example, this is I don't know, D. So when the first person goes from point C to point D, the second person must return from point Q to point R. And then when he keeps going up, he can go up again. So maybe at this point, when the first person arrives at E, this guy return to Q again. Okay, this is clear. So this is the only way. So now he can go up until here, and he go here. But now this guy, if he wants to move forward, he cannot go upper. You see, when the first guy arrived at point F, and the second guy arrived at point P, and they keep moving. If the second guy keep moving forward around this direction, the first guy has to return. And maybe this guy arrived at here. Let's call it, I don't know, L, point L. and this guy return to this point. It's pretty complicated. And finally, they can go together until this point. So, for example, this is called M. This guy, first guy go from M to the point, I don't know, X. And this guy goes from L to X. And they meet at X. And then they kind of change position. The first guy keep moving forward around this direction, and the second guy keep moving around this direction. I think you can believe me if they can meet and basically reverse all the procedures. They can, in the end, the first guy arrive at here and the second guy arrive at here. So the question is, no matter how the shape is the mountain, can this always be done? Is it true? Question. That always the two people can switch position no matter what is the shape of the mountain. Okay, so it's at first glance I don't think it's a very simple problem. At least I have no idea how to do this when I solve this problem. The problem is clear? So if you play with some specific graphs, mountains, you can do it like what I did. But how to prove this rigorously? For any mountain, any shape, you can do this. So this is the place where graph theory comes in. So what we do is the following. We will construct a graph. So we will find all the important pair of positions. So what are important pair of positions? Let me draw some mountain, much more complicated. So here I have a mountain. So let's say something like okay, I start with A, and somehow I arrive at let me say something like this. Okay. So this is S, this is A, and I have many points. Here I call G, and maybe I have here I call P, and here I call Q, and here I call R. So I find this kind of what do we call a tuff, and here is called a peak, and other places this place is a slope. It's like in the middle of a mountain. There are three possibilities. So I found this kind of lower point, and let me forget this word. I'm not very familiar with this tuff. This is kind of it means that lower point, and I draw the same altitude. And when I find some intersection, I mark it as a special point. So this is R. Actually, this R is exactly the same altitude with P. Here, suppose that the point A has the same altitude with S, which is the altitude is 0. And for example, I look at point G. I draw this line with the same altitude, and somehow I find the point O. Suppose Q is lower than O. So maybe.
Dá para apertar Ctrl Z, eu acho, para voltar.
Tudo bem. Eu não sei como faz isso. Mas
Eu acho que na parte superior esquerda também.
Okay. Mas tudo bem. Eu acho que consegui. Aqui é here I have point C, and here I have point D. The point D comes from this lower point. This is L, and I draw this. I found D, and maybe this is F, and this is H, and here I find point N. Okay, and this peak I call point M. Okay, somehow it's just a coincidence. In this example, this point E and M are in the same level. Okay, it's just a coincidence. And here I have point I and delta J and K. Okay, just what I'm doing, I just explain what I want to do. It's not so important. This specific picture is not so important. What I want to do is that I found these special points, and then I draw level line, and I found all the intersections, and all these things, all these points, there are finite of them, are special points. Okay, so my graph is a kind of strange graph. The G, so I define this graph G. It has vertex set and edge set. Vertex set V of G are pairs of my special points. So it consists pairs of these special points. For example, AS is one vertex here, so it belongs to VG. And another one, for example, BP, any pair, BP. Okay, or I can put BR. So here, this is Q here, and this is R. So I need, so how do I find these pairs of special points? They must lie in the same level. Okay, for example, I can also put PR, or RP, doesn't matter, there are many of them, but there are finitely many of them. It can be RB also. So for any level line, if I, for example, have 3 vertices, I can choose any possibilities. I can also, for example, take a CC. Okay, so it can be a pair of the same vertices. Could be a pair of the same vertices. You can choose 2 vertices, 2 points the same. But in the end, there are finitely of them. So this is my graph vertices, and the edge set. So given a pair, for example, I have a pair AS, A here, S here, and BR. It's if you look at the picture, it's a positions of the 2 people, possible positions. And if I look at my graph, I say they form an edge if the 2 people A and B can move from positions AS to BR in one step, so-called one step, meaning that it's allowed by our rules that the first person A and the B, they move from the position AS to BR. In this case, they can locally they can move. There's no problem. They can move from here to here, and from B from here to here at the same time, because they keep the same altitude, the heights. Okay, I think it's pretty clear, the definition. For example, AS and BP does not have an edge. Because if A stands in here and B stands in here and A moves to B, there's no way the second person B moves from position S to position P. Okay? So given these pairs, we only put edge when the two people can move one step from the first position pair to the second position pair. Okay, I have notes. It's actually this last example of my notes. But I want to leave it as an exercise to check the following. So the first thing, degree in this graph, degree of AS is 1. And it also equals the degree of SA. So suppose at some point the first person is in this position and the second person B is in this position. So there is only one way to arrive at that. So they only, for example, SA only join RD. So it has degree 1 in this graph. Now here, in this case, AS has only 1 degree. So its neighbor is only BR. There's no other neighbors. Another thing is that if so let me look at these two positions. For example, I have a vertex as xy. If xy is of peak type, in this case, EM. So EM pair is peak type. So E is a peak, is a local maximum. M is also a local maximum value. Okay? So in this case, check that degree of this guy xy is 4. Because this guy will, let's say, what's neighbors of EM? I say DL. So suppose the two people standing at DL, they can move together to EM. No problem, right? So DN also correct. And FL and FN. So he has 4 neighbors. Is this clear? I think this is the most important thing in this problem. Is this clear? Okay, great. So if you accept this, which the second, it's easier. If other situations are easier, of the type peak, what you call tough, and I don't know what's the word. Let's say lower point. This type. What's the degree? It's also 4, okay? It's also 4. Do you have a lower lower point. No, I don't have two lower points, but the proof is similar. But if xy is of peak and slope type, then I claim that the degree of xy is 2. Not instead of 4, it's 2. So what happens is that here it's I don't know where is the peak. Here is a peak. For example, here E is a peak. Point K is a slope. So it's in the. So let's look at. I hope you remember this. I'll clean this and to make some space for me to write down. For example, if I have a point EK, it will join an edge to DL. Okay? And also FL. So exactly because here you have two choices, it's a peak, you have two direction to go. But both two directions, the altitude must decrease. So it means for K it has only one direction to go. So you can see it has degree 2. And there are some other similar situations if xy is of, for example, low point, and slope type, then the similar computation gives you the degree of xy is 2 again. So to sum up, maybe it's not complete. There are several other cases, but if you look at the situation, only in case 1 you see degree 1, and all other cases you see an even degree. It's either 4 or 2 or 0. There is a possibility you don't have a. There is a possibility you don't even have any degree. So what is the possibility? Suppose G and the Q are at the same level. So the point GQ is allowed to be defined as a vertex of the graph. But however, it has no edge. It is an isolated vertex. Its degree is 0. Because here at the point G, he can only go up. And here at the point Q, he can only go down. So what it means that there's no other vertices you can join. So degree of this guy is 0. After this list of degrees, different cases, different situations, you can see that only case 1 you observe 2 vertex with degree 1. Okay, so to sum up, in this graph, there are only 2 vertices, AS and SA, which have odd degree. All other vertices have even degree. In fact, they only can have degree 0, 2, or 4. Yeah, these are the only possibilities. Okay, what can we say about this? So if a graph here, you can look at any graph, you can consider the so-called connected components. So here is a graph. you have I don't know, something here and something here. So this is a connected component, this is a connected component. They are not connected. Okay, so this is a notation maybe I forget to say before. It's not a very difficult notation. So from what we have been observing, we know that the 2 points AS and SA must belong to the same connected component. Okay? If not, it's not possible. If they belong to 2 different connected components, then take the first connected component. We only find 1 vertex without the degree. We have proved a theorem or its corollary. I think I also put it in your second list to reinforce this because it's important. The number of vertices without the degrees must be even in any graph. But if you have a connected component, you look at this connected component, it is a graph itself. And this graph only have 1 vertex. For example, AS, it has degree 1, it has odd degree. It's not possible. So since the whole graph, we only have 2 vertices without the degree, so they must belong to the same connected component. Then, meaning there exists a path connecting AS to SA. What is a path? I already explained to you. Here it is a path. From V0, V1, V2. So here is a path in graph. For example, V4. Here V0 is AS, and V4 is SA. So if you exist such a path, since there exists such a path, then you can just follow the path from V0 until V4. Or you follow the path, you start from AS and you arrive at SA. So what did you do if you follow the path to walk from this end to another end? You have exactly a method for 2 people to move along the mountain and change position. Okay? So this is the proof, more or less. This is the first example I want to say. Is it clear for you? I already included this in the in my first notes, but I think I hope it helps if I explain now. So this example means that there are problems really not easy to relate to graph theory, and if you are able to use graph theory to solve it, it's very beautiful, very interesting. It's just a translation of a problem into a graph theory language, and you use this simple fact that in a graph, the number of vertices with odd degrees is even. Only this, and you must connect these 2. Only vertices with degree 1 with a path. And then you translate back. It means that you can find a way to change position for these 2 people. I think it's the most complicated problem in this lecture, and okay. You can think a little bit, and maybe we can discuss more if you find it's not very convincing. Okay. So we continue working with degrees. Let me explain another problem, which is and which I found interesting. Also, not very easy to translate it into graph theory language. So a triangle. So problem 2. Suppose I have a triangle in the plane. A triangle. Maybe I call it ABC. Maybe I don't put any name in the plane. And not only that, I have a triangulation of the triangle. What is triangulation? It's something like this. Let me draw this triangle bigger than. I have a triangle. Let's draw this triangle bigger. And have something I call the triangulation. So, for example, this. So I just put some points here, and I split this triangle into smaller triangles. Something like this, and have something like this. So this is not a triangle, but I'm not finished. So, okay, so here is another triangle, here is another triangle. Maybe I put one more edge here, and here. Okay, and somehow I put something here, and maybe something here. Okay, now everything is split into smaller triangles, right? So what I do is that I want to use 3 colors to color the vertices, to color the points. All the points, special points, this kind of points. This point, this point, this point. I want to use 3 colors. To color the points in this triangulation. Okay, maybe I put C1 here, and with the condition that the initial 3 points here use different colors. So I start with C1, C2. So with the condition that how to say this? So let's say here is a point A, B, and C. I put A has color C1, B has color C2, and C has color C3. Okay? This is my point B. This is my point A. C1, C2, C3. So C1, C2, C3 are 3 colors. And then I arbitrarily put other colors for these points. So conclusion. So that there must exist a small triangle whose 3 endpoints have different colors. So I must find some triangle. For example, here is another point. For example, this triangle. For example, the 3 points have different colors. So this is the conclusion. So in the beginning, I mean the bigger triangle, I have different 3 colors. And there's no restriction for other points. So conclusion is that I must find a small triangle. Also, it has 3 different colors for its endpoints. Okay? What is happening here? Yeah, right, okay. So the proof is as the following. It's a little interesting. How to use graph theory to do this? It's very interesting. So given the coloring, let's say the coloring is given. Of the vertices, of the points. So let's say the color is given. And then we will draw something called a dual graph. This notion will become important later when we study planar graphs and the full color theory. So how to define it? But it's not completely the same thing. It's here. It's a little variation of the standard dual graph. So what do we do? For example, let's observe a local situation. Suppose we have 2 triangles like this. If we find C1 here and C2 here, we will draw. So every triangle I'll put it. So what's the graph? The vertices of the graph is every triangle. So for example, this triangle represent a vertex of the graph. This triangle represents a vertex of the graph. They have an edge if and only if this. So their boundary, this edge, you see C1, C2, 2 colors at the endpoints of this edge. Is it clear? So here is V1, here is V2. Each Vi is just a small triangle. So every small triangle is a vertex of my graph. But there is an extra vertex which I put here. I call V0. It's not a triangle, but the remaining vertices are just all the triangles. For example, here I have V0, I have V1, V2, V3, V4, V5, V6, V7, V8, V9, V10, V11. In this example, I have 11 vertices. And I have some coloring. For example, here maybe it's C1, I don't know. Maybe this here is C2. Maybe here is C3. I don't know. I don't care. So I only look at local situation. If 2 triangles, V1 and V2, their boundary, which is an edge, which is a line segment, and its 2 endpoints are colored with C1 and C2 and put an edge. For example, here, if you have some situation C1 and C1, I don't put edge. If it's C2, C2, I don't put edge. If it's C2, C3, I don't put edge. I only put edge here if you see C1, C2. Is it okay? Yeah. So let's see what's happening. Here, I found let's use red. Here I found an edge C1, C2. So it means that there is an edge joining V0 and V1. Because this edge is C1, C2. And this is the only edge connecting V0. Because here is C1, C3, no edge here, no edge here. here is C2, C3, no edge here. So V0, there is only one edge connecting V0 to V1 here, because I see C1, C2. And later, what I want to observe is the following. If I have V1, if I have a small triangle colored with C1, C2, and C3, and maybe this triangle I call VK. VK exactly has, so degree of VK is 1. Okay, so this VK must join edge along this line segment because it's C1, C2. It doesn't join here, doesn't join here, so dVK is 1. We already know that dV0 is 1. And if other situation, for example, I have something C2, C3, C3, then this vertex has no edge. It cannot join other neighboring triangles because there is no C1, C2 edge. Another situation, if I have C1, C2, C2, then this guy has degree 2. Okay, so let's call Vi. Let's call this Vj. So what I'm saying is that dVi is 0 and dVj is 2. So here, to sum up, something similar is happening. I think this is similar and simpler than the previous problem. dV0 is 1. And if I see picture 2 or 3, so let's say dVk is odd if and only if this triangle, this small triangle, used 3 different colors. Okay? So because there are only 3 situations, only this situation, when this triangle use 3 different colors, the degree is odd. This is even and this is even. But however, we know that V0 has degree 1. So we conclude, so we use this proposition again. Okay? The number of vertices with all the degrees must be even. We already have 1, so it means that there must exist some vertex Vk such that the degree of Vk is odd. In this case, its only possibility is it equals 1. And then we find a triangle with 3 colors. Okay? Is it better than the previous problem? Okay, great. So I think it's very interesting, but the difficulty is usually how do you integrate the problem into a graph theory problem. If you can do it, it's very nice. The tools, the theorems you use is very simple. Just I repeat this many times. Just the number of odd. Sometimes you call vertex with odd degree an odd vertex. So in this case, you say that the number of odd vertices is even. Okay. So let me finish today's lecture with another third example, which is it's simpler than the previous two. So it also asks you to play with degrees, But okay, it's a familiar topic. Uh, I think maybe many of you have already heard of it. So let's talk about this problem. Okay. So let's put a theorem on it. So there are 6 people. It's very simple. I think it appeared in some kind of Olympiad mathematical contest maybe many years ago. So now because it's a standard, it's become too simple to put it. So any 6 people, either 3 of them know each other, or 3 of them do not know each other. Okay. Let me ask you something. How many people have heard of this before? So let me try. Uh-huh. Sim, sim, essa gravação eu vou postar na YouTube, de fato. How many, this problem, have you heard of this? No? I saw a problem yesterday. Yesterday? That's interesting. So, okay, it's a kind of classic problem. Let me explain what's the point of this. It's not so difficult. So the proof is, let's say, how to imprint again. How to imprint this? So I have a graph G with 6 vertices. So let's say it has VG equals V1, V2, V3, V4, V5, V6. Okay? What happens is that I can use 2 colors, like red and blue, to give any. So what happens is that you can choose an edge between 2 vertices if they know each other, and there is a non-edge between 2 vertices if these 2 people don't know each other. But you can do it another way. You can put a red and a blue to make the situation more colorful. So red means an edge, blue means a non-edge. So for example, I fix a guy, V1. So there are 5 other guys, V2, whatever. So there are 5 other guys here. There are 5 other guys in this rectangle. So I have to consider everyone. So V2 knows V1 or not, V3 knows V1 or not. I consider every pair. So I claim that by pigeonhole principle, I claim that at least 3 people have the same state with V1. What I mean is that maybe I have 3 people, V2, V3, V4, they know V1. And the other 2 rest, the other 2 doesn't know V1. It can be larger. Okay, what I'm saying is that either more than 3 people, at least 3 people, more than 3 people know V1, or more than 3 people do not know V1. Okay, this is just a pigeonhole. So know, I put color red. Doesn't know, I put color blue, for example. So in this case, what happens is that I have, maybe I really draw the color. So here, in the first situation happens, for example, I have 3 blue. Okay, maybe 2 red. So 2 people don't know him. So here I have V5 and V6. Because this is a claim, you can prove it by pigeonhole. So I just fix one situation. Other situations you can discuss in a similar way. So I just say, okay, let's fix one situation. that three people, at least three people know V1. So what happens is that V2, V3 must have a red edge, because if V2, V3 also know each other, then we are done. We finished, because we find the three people who know each other. Okay? The conclusion is that either three of them know each other, or three of them do not know each other. So if really V2, V3 is a blue edge, what I'm saying here is blue. Sorry, I think what I'm confused with. I'm confused with the color. So here is blue. Here is red. Okay. So continuing with this picture, if V2, V3 has a blue edge, then I have found a blue triangle. So the three of them know each other. So I conclude that then we are done. We are finished with the proof. So we can say, okay, they have a red edge here. And the same thing happens with V3, V4. If V3, V4 has a blue edge, then I have found a blue triangle. So I conclude V3, V4 must have a red edge. They don't know each other. And the same thing happens with V2, V4. If V2, V4 know each other, we put a blue edge. It means that V1, V2, V4 form a blue triangle. So in this case, we are done. We finished the proof. So we conclude that V2, V4 must has a red triangle. But now we have a red triangle. So this is the argument. So we conclude that V2, V3 must have a red edge. V2, V4 must have a red edge. And V3, V4 must have a red edge, which is very strange, because here it implies that V2, V3, V4 is a red triangle. Then we translate language back. It means that the three people, they don't know each other, and we are done. Okay? I think this is not very difficult. Okay? I think most people should follow this. Okay? Yeah, of course. This is it's not difficult. But I want to say something more. So not only about this course. So we are basically finished with today's three examples, and but I want to say something more. So something more difficult. So it's not required in this course, but I cannot resist to talk about this. So this is something called the Ramsey theory. It can be more complicated. So this what happens is that more formally we define RKK to be the minimal integer n, such that any two coloring. So I explained this example exactly in order to prepare for this definition. Any two coloring of the edge set of the complete graph on n vertices. So this is the example gives you a complete graph on 6 vertices. And I'm talking about complete graph on n vertices. N could be large. So any two coloring of a complete graph, vertices, the edge set of Kn. Let's write it as using, for example, using two colors. Using colors C1 and C2, like before, blue and red. Okay, but here I'm writing RKK. two integers, rkk. Either there is a copy of kk, complete graph with k vertices, with all edges, colored C1, or there is a copy of kk with all edges colored C2. So it's a very long definition. So what happens is that I suppose that there is an integer n, and I consider the edge set of the complete graph on n vertices using two colors. And all these are satisfied. Either there is a copy of kk completely colored with color C1, or there is a copy of kk completely colored with color C2. And so what happens is that people can prove that such n always exists, and it's a finite number. And I'm looking for the minimum n to satisfy all this. So this is the definition of RKK. So it's a Ramsey number. Some call this diagonal Ramsey number, because sometimes people also consider, for example, R3, R34, two different integers. I'm looking for blue K3 or a red K4. It's not necessary these two numbers are the same. But here I'm only talking about RKK. So I'm looking for a blue KK or a red KK. So when n is large enough, you can find this. What I proved in the previous example is exactly R33. This guy is smaller or equal than 6. Because if I put 6 integers, I can do this. Either there is a copy of a triangle, blue color triangle, or a red color triangle. But this is only half of the proof. They only can prove that R33 is smaller or equal than 6. To prove that R33 is greater or equal than 6, you have to actually, indeed, R33 equals 6, but my proof is not complete. To prove that it is also greater or equal than 6, you have to actually give an example of a coloring using 5 vertices, such that there is no copy of blue triangle and there is no copy of red triangle. So you find the example to find the lower bound, and to make some arguments, some analysis, kind of this kind of logic to give upper bound. In the end, you prove what is R33. So this kind of problems has a very huge history, and it's a research area, very active research area. For example, it's very recently, a group of mathematicians, basically both based at INPA, they proved there is a, for example, it's long no, I don't know, 60 or 70 years old. People know that RKK is always smaller or equal than k to the power of 4 to the power of k, and greater or equal than something like square root of 2 to the power of k. They use some kind of tools. It's beyond the scope of this course. But this bond cannot be improved. So I don't know. This is it's really, I don't know, 1940s. It's really old. And it cannot be improved for, I don't know, 70 or many years, 80 years, I don't know. So very recently, there is a theorem proved by a group of 4 people. So let me write their names. I don't know if I think I remember the names. So Campos, Simon Griffiths, Marcelo Campos, Robert Morris. and I have difficulty to pronounce it name. So I'm sorry for him. So they improve this bound to something 4 minus epsilon to the power of k. Only this. But this epsilon is some very specific number. So this is still not published, I think. So it's submitted to RK last year. It's a huge progress in this area, and considered one of the most important results in the year of 2023. So I think it's a very nice area. So you are young students, you are very young, and maybe some of you in a few years can get into this area and work on this. Who knows? It's very exciting, and there are many nice people. In particular, these 4 people, 3 of them are there is 2 professors in Brazil, 1 graduate student, and another professor from, I think he's from Cambridge, but he came to IMPA to do a postdoc. But this group of people really, they are based at Brazil. Okay, you know this? Do you know this? Have you heard of this? It's on the news all the time from last year. Okay. So have any questions? Let me finish the recording for today. Okay. So